The National Electrical Code, or NEC, addresses the installation of cables and raceways in walls, specifically in Section 300.22c. This section states that cables and raceways should not be installed in narrow voids within masonry block or tile walls, nor within hollow spaces in walls or ceilings of combustible construction. An exception exists when such spaces are accessible for future maintenance or inspection. This provision covers low-voltage 24 volts wire such as the 8-conductor plenum-rated wire used for card readers. Therefore, you may install it in sheetrock walls without a raceway if some conditions are met. Firstly, the wire must be installed in an accessible location. Secondly, the wall cannot be of combustible construction, meaning it needs to be made of materials like drywall or plaster. Thirdly, the wires must be protected from physical damage, perhaps by installing them in a sleeve or conduit. There are exceptions to this rule. One exception is when wires are installed in a prefabricated assembly that has been listed and labeled for the specific use. Although the NEC does not strictly mandate raceways for low-voltage 24 volts wire in sheetrock walls, their use is generally recommended for several reasons. Firstly, raceways offer physical protection to the wires against damage and interference. Secondly, raceways enhance accessibility, simplifying future maintenance and inspections. Thirdly, raceways aid in separating different types of wiring, which reduces the likelihood of interference and electrical hazards. It is also worth noting that other NEC sections may apply depending on the specific type of wiring and the environment in which it is installed. For example, if the wiring is installed in a wet location, it must be listed for wet locations. Always consult the latest edition of the NEC and local codes for the most up-to-date requirements and regulations. When dealing with electrical installations, you need to consider voltage drop. Voltage drop is the decrease in voltage along a conductor due to the impedance of the conductor and the current flowing through it. Excessive voltage drop can cause equipment to malfunction, overheat, or fail prematurely. The NEC provides guidelines for minimizing voltage drop in branch circuits and feeders. For branch circuits, the NEC recommends a maximum voltage drop of 3% at the furthest outlet for power, heating, and lighting loads, or combinations of these. The maximum voltage drop for feeders should not exceed 2%. The total voltage drop from the source to the furthest outlet should not exceed 5%. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, which represents the resistance of 1 circular millifoot of copper conductor. For copper, K is typically 12.9 ohms. I is the current in amps flowing through the conductor. D is the one-way distance in feet from the source to the load. Cm is the circular mil area of the conductor. When selecting conductors, ensure that they are properly sized to minimize voltage drop and prevent overheating. Consult NEC tables such as Table 310.16 for allowable ampacities of insulated conductors. Consider factors such as the ambient temperature, the number of conductors in a raceway or cable, and the termination temperature rating of the equipment. Overcurrent protection is another critical aspect of electrical installations. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. The NEC specifies the requirements for overcurrent protection in Article 240. The general rule is that conductors must be protected against overcurrent in accordance with their ampacities. The overcurrent protection device should be sized no larger than the allowable ampacity of the conductor it protects. There are some exceptions to this rule, such as when the conductor is part of a motor circuit or a tap conductor. When selecting overcurrent protection devices, consider the interrupting rating, which is the maximum fault current that the device can safely interrupt. The interrupting rating must be sufficient for the available fault current at the point of installation. The NEC requires that overcurrent protection devices be readily accessible and not exposed to physical damage. They should also be properly labeled to indicate their ampacity and interrupting rating. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, allowing the overcurrent protection device to trip and to energize the circuit. Bonding connects all non-current carrying metal parts of an electrical system to create a low impedance path for fault current. The NEC requires that all electrical equipment be properly grounded and bonded. The grounding system should consist of a grounding electrode, such as a ground rod or a metal water pipe, and a grounding electrode conductor that connects the electrode to the service equipment. The bonding system should consist of bonding jumpers that connect all metal enclosures, raceways, and equipment together. The size of the grounding and bonding conductors is determined by the size of the service conductors. Refer to NEC Table 250.122 for the minimum size of equipment grounding conductors. Proper grounding and bonding can help prevent electrical shock, fire, and equipment damage. Wiring methods are the techniques and materials used to install electrical conductors. The NEC specifies various wiring methods, each with its own set of requirements and limitations. Some common wiring methods include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, flexible metal conduit, non-metallic conduit, cable trays, and various types of cables. The choice of wiring method depends on factors such as the environment, the type of occupancy, and the voltage and current levels. Each wiring method has its own set of installation requirements, including the spacing of supports, the bending radius of conduits, and the securing of cables. Always follow the manufacturer's instructions and the NEC requirements for the selected wiring method. When installing conductors in raceways, it is important to consider the fill requirements. The NEC limits the number of conductors that can be installed in a raceway to prevent overheating and to ensure that the conductors can be easily pulled in and out. The allowable fill depends on the type of raceway, the size of the conductors, and the number of conductors. Refer to NEC Chapter 9 for the fill requirements for various types of raceways. When pulling conductors into raceways, use a lubricant to reduce friction and prevent damage to the insulation. Avoid overfilling the raceway, as this can make it difficult to pull the conductors and can also cause overheating. Electrical boxes are used to terminate and splice conductors, as well as to provide a mounting location for devices such as switches and receptacles. The NEC specifies the requirements for electrical boxes in Article 314. Electrical boxes must be of sufficient size to accommodate the conductors, devices, and any necessary splices or terminations. The size of the box is determined by the number and size of the conductors entering the box. Refer to NEC Table 314.16 for the minimum box volume requirements. Electrical boxes must be securely mounted and properly supported. They should also be accessible for future maintenance and inspection. When installing conductors in electrical boxes, ensure that the conductors are properly stripped and terminated. Use wire connectors that are listed for the type and size of conductors being used. Securely tighten all connections to prevent loose wires, which can cause arcing and overheating. Arc fault circuit interrupters, or RFCs, are designed to protect against electrical fires caused by arc faults. An arc fault is an unintentional electrical discharge between two or more conductors. RFCs detect arc faults and quickly de-energize the circuit, preventing a fire from starting. The NEC requires RFCs in many areas of the home, including bedrooms, living rooms, dining rooms, and kitchens. There are two types of RFCs: branch circuit RFCs and combination RFCs. Branch circuit RFCs protect against arc faults in the branch circuit wiring. Combination RFCs protect against both branch circuit arc faults and series arc faults, which can occur in appliances and cords. When installing RFCs, follow the manufacturer's instructions and the NEC requirement. Test the RFCs monthly to ensure that they are functioning properly. Ground fault circuit interrupters, or GFCIs, are designed to protect against electrical shock caused by ground faults. A ground fault is an unintentional electrical connection between a live conductor and ground. GFCIs detect ground faults and quickly de-energize the circuit, preventing electrical shock. The NEC requires GFCIs in many areas where there is a risk of electrical shock, such as bathrooms, kitchens, outdoors, and near swimming pools. GFCIs are typically installed in receptacles or circuit breakers. When installing GFCIs, follow the manufacturer's instructions and the NEC requirements. Test the GFCIs monthly to ensure that they are functioning properly. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges. Voltage surges are temporary increases in voltage that can damage or destroy sensitive electronic equipment. SPD diverts surge current away from the equipment, protecting it from damage. The NEC recommends SPD for all electrical services. There are two types of SPD, Type 1 SPD and Type 2 SPD. Type 1 SPD are installed at the service entrance and provide protection for the entire electrical system. Type 2 SPD are installed at the branch circuit level and provide protection for individual circuits or equipment. When installing SPD, follow the manufacturer's instructions and the NEC requirements. Regularly inspect the SPD to ensure that they are functioning properly. Electrical safety is paramount in any electrical installation. Always follow the NEC requirements and the manufacturer's instructions. Use qualified electricians for all electrical work. Energize circuits before working on them. Use proper personal protective equipment such as insulated gloves and safety glasses. Inspect electrical equipment regularly for damage or wear. Replace any damaged or worn equipment immediately. Never overload circuits or extension cords. Keep electrical equipment dry and away from water. Teach children about electrical safety. By following these safety precautions, you can help prevent electrical accidents and injuries. Always consult the latest edition of the NEC and local codes for the most up-to-date requirements and regulations. Electrical codes and standards are constantly evolving to reflect new technologies and safety concerns. Staying informed about these changes is essential for ensuring that electrical installations are safe and compliant. Consider attending continuing education courses or seminars to stay up to date on the latest electrical codes and standards. Join professional organizations such as the International Association of Electrical Inspectors or the National Fire Protection Association to network with other electrical professionals and stay informed about industry trends. Subscribe to industry publications and online resources to stay abreast of the latest developments in electrical codes and standards. By continuously learning and staying informed, you can ensure that your electrical work is always safe, compliant, and up to industry standards. Always refer to the authority having jurisdiction.